which is an animation into research on aerodynamics by the Susi Earnshaw Theatre School. So over to you, school.
Greetings, SSC. For our project, we decided to create and test 3 paper planes in order to learn more about aerodynamics and how to make planes better. All our models are variations of a single design, each one with its own distinct features, so that we can observe the effects of different designs on an aircraft. We are joining you today in virtual reality, as we thought it would be fitting, seeing as everything this year is virtual. We hope you like our project, and in the single week we had to do this, we tried our best to fact check and explain why each design might fare differently.
To understand how different paper aeroplane designs affect each of their destinations, we must first understand how an aeroplane actually works. First of all, there are 4 basic types of forces used by an aeroplane: lift, weight, thrust, and drag. And lift is the force that makes the plane go upwards, and weight is the force that makes the plane go downwards and is affected by the gravitational field of our planet. And thrust is a forward motion and makes the plane go forwards, and drag is the opposite to thrust. I am an artist. My drawing skills are legendary. The shape of the wings makes it so it catches more air under the wings than above the wings. This results in a high pressure of air under the wings and a lower pressure of air above the wings. This creates an upwards lift of force. On aeroplanes, this force must exceed the downwards force of the weight of the plane to a point where the 2 forces repel from each other and the plane lifts off the ground. This is a result of Newton's third law of motion.
If we add Bernoulli's principle into the picture, we also find out that the wings are in a certain shape, which results in fast-moving air above the wings and slow-moving air under the wings. This is very important for a plane, as slow-moving air results in a higher pressure than faster-moving air, which would result in more lift. Without this principle taken into account, it would be a lot harder to produce lift on aeroplanes. To get the maximum amount of distance, once a plane is at its highest point from the ground, the weight and lift of the object must level out and thrust must be greater than drag, assuming that the greater level of thrust has no effect on lift, and that you have a constant and infinite level of thrust. You can technically fly at a constant speed and level forever. So why can't we achieve this on a paper aeroplane?
The reason why we can't is that we don't have a constant level of thrust. Assuming that there is no wind blowing in the direction of the throw, the only thrust we have is from the power of our arm that we use to throw the paper aeroplane. After we throw the object, the force of the thrust in the object will dissipate, and drag will eventually overcome the force of thrust, and the paper aeroplane will hit the floor. As the paper aeroplane hits the ground, the force of the weight will result in kinetic energy being lost, as friction between the floor and the object will result in kinetic energy being wasted to a transfer in the thermal energy stores of the floor.
Many people have used science and aerodynamics to create the best paper aeroplane possible. There is even a world record for the furthest paper aeroplane thrown. Scientifically, the best paper aeroplane would have to be the design where the level of thrust and the level of weight are equal for the majority of time that the object is in the air. As the weight of a full-sized aeroplane is very heavy, the amount of lift must be extremely great to overcome the downwards force of an aeroplane. To achieve this, the amount of lift from the air pressure under the wing of the plane is supplied and assisted by the thrust of the object. The thrust from the jet engines on either side of the plane, which push the plane forwards, also assists the amount of lift exerted from the back of the plane. As the jet engines are positioned in a way that the air that comes out of the back of the jet engines also is caught under the wing to increase the air pressure even more, as not to waste any energy that could be used. As the design of the plane means the 2 forces, thrust and lift, would work together to overcome the force of the weight of the plane. If you fold the tips of the wings like this, you can reduce the amount of wingtip vortex there is. Reducing the wingtip vortex also reduces drag. But what is wingtip vortex?
Well, wingtip vortex is when the air from below the wing, which has a high pressure, moves to the top of the wing. This can form a swirling tunnel of air off the tips of the wings. This swirl of air can continue for several minutes. This air off the end of the wing of the plane can result in a reduction in air pressure under the wing as more air is lost. This causes extra drag on the aircraft. The heavier an aircraft is, the stronger the effect of wingtip vortex there will be. Luckily, paper is very light. Also, when lift on a plane's wings increases, so does wingtip vortex. To reduce this, engineers and mechanics have created winglets that go on the edge of planes' wings. This results in the air coming up from below the wing getting caught and trapped in these winglets. The winglets also add stability to the object. Wingtip vortex can also reduce the effectiveness of the angle of attack, AOA. This is the angle at which a plane must sit to get a constant level of flight, which means that the force of lift and the force of weight of the plane are equal. Wingtip vortex can reduce the angle of attack, which results in the lift of the plane reducing, which means that the plane will take longer to climb in altitude.
In our experimenting, we made a prototype that was turning to the right a lot and spinning out of control. On further inspection, we found that the left wing was just about a millimetre longer than the right. This meant that the left wing had a lot more lift than the right wing, as there was more surface area which resulted in more air underneath the left wing than the right wing. So it tipped the plane over on its side, showing us just how exact we had to be. One of our planes used something rarely used on paper aeroplanes. We put a spoiler on one of them, so it would gain extra lift, meaning that it would naturally fly upwards, extending its time in the air. However, we were unsure whether or not it would end up slowing down the plane, with our theory being that it would. We felt like it would have too much lift, as paper is so light compared to something like a real plane would be made out of, and it would also cause a lot of drag. But we did think there were some benefits to the spoilers, one of them being that when the paper aeroplane had reached its maximum height and started to fly down, spoilers would catch more air and push the back of the paper plane to a more level position, in line with the front of the plane. We also predicted this would happen to paper aeroplane 2, one of the wingtips.
Our three designs that we chose for our paper aeroplane are as follows. Paper aeroplane 1, your average paper aeroplane. Paper aeroplane 2, your average paper aeroplane but with winglets. And paper aeroplane 3, your average paper aeroplane but with spoilers. We are going to rate the three planes on speed and distance to work out which one is the best.
Our guesses for the fastest aeroplane went aeroplane 1, aeroplane 2, and in last place, aeroplane 3. We also made guesses on the aeroplane that would go the furthest. In first, we thought aeroplane 2, then aeroplane 3, and last but not least, aeroplane 1 in the last place. In our test, we used a sheet full of 2.19-inch squares to measure the speed, recording in slow-mo at 240 frames per second. And however many boxes the aeroplane crossed in 1 second in slow-mo, that will result in the miles per hour the plane went. We got people to help us hold up the sheet of paper, and after that, used a rubber band to launch each plane at an angle of 45 degrees to ensure consistent results. The paper plane that travelled the furthest was aeroplane number 2 at 9 meters and 89 centimeters. In second place we had aeroplane 3 at 7 meters 95 centimeters, and in last place we have aeroplane number 1 at 6 meters and 44 centimeters.
In our speed test, our first place was airplane number 1 at 21 miles per hour. Our second fastest, airplane number 2 at 19 miles per hour. And at last and very much least, airplane number 3 at 17 miles per hour. Number 2 is the best all-round plane, sacrificing a tiny bit of speed for extra stability and all-round good distance beats our other 2 designs by a long shot. Thank you all for listening.
And I hope you all learned a little bit about how planes work. Goodbye.
Bye-bye.
Well, thank you very much there for that intriguing animation, an unusual take on the subject. Do we have people ready at the school to answer questions?
Yeah, we do.
You are, that's lovely. That's lovely. Could I ask why you chose this topic?
Because we only had a week to do this project and we needed something to display aerodynamics and physics in general that wouldn't take too much time.
We were very interested in the subject.
Okay, thank you. I've got a question from chat. Somebody asked, how did you go about collecting research for your project?
It didn't really show up on the video, but if you'd see the paper, it's got squares that we use to measure the speed and distance of each plane. A lot of the facts we got from various websites, some of which were independent, others from corporations that surprised me, like NASA.
That's interesting. So somebody's asked, if you did the experiments again, is there anything that you would do differently?
Yeah, we would spend more time making sure we're controlling as many variables as possible, because that may have had an effect on the experiments.
Thank you. And they also asked, are there any other design elements you might test out?
Yeah, we were planning to try different planes with different wingspans to see if they would be able to generate any more lift and therefore get further.
Okay. So a question, why is it important to have more pressure under the wings?
Because the more pressure under the air wings results in more air under the wings.
It results in a higher lift, meaning that the weight of the plane or whatever it is will be combated more, and it'll be a lot easier to get it off the ground and remain in the air.
Thank you. You mentioned that paper planes can go a very, very long way. I don't think I noticed it. Do you know how far the longest paper aeroplane flight that's been recorded is?
I believe it's somewhere around 100 meters.
Yeah, I think it was just over 100 meters.
That's a very impressive paper aeroplane flight, I've got to say. It was interesting that your designs, the fastest or longest travelling one was the one without the wingtips being turned up, yet commercial aircraft do have wingtips turned up. Do you know why this is?
Because the one that did have the wingtips turned up had a far smoother and longer flight, meaning that it was using the energy given to it by the launch far more efficiently. And by the reduced wingtip vortex, it could continue using its lift with a minimum amount of drag.
The simple design of the original paper airplane was more like a dart than a paper airplane, so there was much less drag on the paper airplane, so it kind of acted more like a dart.
Thank you. I've got a question in the chat box again. Did the planes fly in a straight line, and which design had the straightest flight path?
They were all shot in a straight line. However, they tended to deviate a bit away. The one that stayed the straightest was number 2, which was the one with the tips messed up. It had the most stable flight. Number 3 had the least stable flight and pretty much turned over in the air straight after it went off steam.
Okay, thank you very much. We don't have any more questions in the box, so I'm going to say a big thank you to all 3 schools for their very different presentations and for talking us through them and doing the questions and answers afterwards. Great jobs done all round. Everybody be really proud of yourself, and thank you very much. We are approaching the end of this session, so thank you all. Well done.
That's great. Thank you very much, Sue, for hosting today. I know you stepped in at the last minute, so thank you for that. Big thank you to the 3 schools, to Central Foundation Girls' School, Claremont High School and Susi Earnshaw Theatre School for presenting today. There was a lot of hard work went into creating those presentations, and it was much appreciated that you made the effort to take part today. Thank you for that. Sue is also on the judging panel to determine who's going to win the Association for Clinical Biochemistry and Laboratory Medicine trophy. She also has colleagues joining her, Manfred Almeida, Microbiology Laboratory Manager at Imperial College Healthcare NHS Trust, and representing the Association for Clinical Biochemistry and Laboratory Medicine is Matthew Whitlock, Principal Clinical Biochemist at Imperial College Healthcare NHS Trust 2. So the judges will be deliberating and we will let you know the results at the end of the day. So thank you all once again. Looking ahead, we're going to take a lunch break now, and then if you can all join us again, please, at 12:50, when Pinky McQuainer will tell us about disciplines and connections. Thank you all.